And yes.
Yes. So, back into shaders, specifically view shaders. Before I start, however, does anyone know what the difference is between a compute shader and a normal shader?
Between a what now?
A compute shader and a normal shader. Right. So, the difference as I define it, I think, don't take this as a sort of the actual definition of a compute shader, because that's not probably the case, but my definition is that the compute shader don't by default have any buffer bound up to it, in the case of Unity at least. So you deal with all the data flowing in and all the data flowing out, and not only that, you define how the data flows in. We'll come back to that. So let's just start. What? Okay, interesting. Yeah, compute shaders in Unity, they're pure HLSL, so high-level shading language. I think it's that's a bit of.
Is it NVIDIA or?
So CG, the one we used previously, is NVIDIA.
All right.
HLSL is Microsoft.
Is it DirectX?
Oh, right, yeah.
What?
What? CG is?
No, HLSL.
Yeah, that's
right. Okay,
but that's
sorry.
by Microsoft, right?
Yeah.
Yeah. So I didn't mention this earlier, but there's a difference there. CG was developed by NVIDIA using sort of the same syntax as HLSL, and their intent was to sort of bridge the gap between GLSL and HLSL. Hence their incredible cross-platform compilability. Yeah, back to this. Yeah, there's it's pure HLSL, meaning there's no shader lab syntax to mess around with. We'll go through this step by step, but first you need to verify that your Unity or your system supports it. So, yeah, if you want to use compute shaders, write this somewhere. Not necessarily the debug message, because that's yeah, not the. So, dissecting the compute shader. To start off with, you need to define what the programming function is. Similar to how you did with the vertex and, well, all the other shaders, you call a pragma, and then you say, or you say pragma kernel, and then there's the name of the shader or the function. So in this case, we have CS main, which is the default name, compute shader main, and it's a pretty simple one. Not necessarily the best use of compute shader, seeing as you're operating with UV coordinates and stuff, but that's yeah, one use of it, I guess. So, yeah, the pragma is just to define the entry point. Then, within this shader, we have a read-write texture 2D, which is different from a normal texture because you can read and write to it. Though you can't do both at the same time in Unity's compute shaders, which is kind of sad. You need to have two textures in order to do some sort of reading and writing operation, also known as double buffering. So yeah, we also need to define sort of the position of the texture. So each pixel, because a texture is really just a buffer, right? In this context, at least, which in this case also consists of code 4. Then there's the big one. This is probably the most difficult one to explain because it deals with how the shader is executed. Therefore, it's also probably one of the more important ones. So I'll try to do it anyways. But before we go into that, let's look at how you would dispatch or run the compute shader. So I've written a simple C# Unity model behavior, where you sort of set up the references, you get this shader. All of these are accessible through the inspector, so you can sort of set them in the editor. And then within the awake call that happens on all model behaviors, I do some setup stuff first, and then I do the dispatch. So first I find the kernel named CS_main, so that is where it shows up again. Then I define a render texture, which is the only type of texture in Unity you can read and write to, but you need to enable this. So I've written enable random write, and then you create it, because you can do all sorts of setup before you actually create it. And then you need to set up the uniforms. I don't actually know if they're called uniforms in this context, but they're sort of a similar concept. So you set up the texture named result in the shader to be the render texture, so this one. And you set the text resolution to be the resolution. So yeah, the UIT texture is now this text resolution. Then we come to the dispatch thing, and does anyone notice anything strange about that, just based on sort of how it looks? Why do we send the specific things we send into the compute shader? Okay, so first off, the kernel ID, right? That makes sense. We need to specify what kernel are we actually dispatching, because you can have multiple kernels or multiple programs, I guess, within the same shader, compute shader file or compute shader asset in Unity. So the second and the third parameters are the ones I'm sort of curious if you see anything weird about. Yes?
Resolution X and resolution Y are both divided on 8, but are ints, so you're going to lose some detail there.
Okay, so you're on to the right thing. Yes, you might lose detail there, but why do we divide by 8 in the first place is also a question I would ask. It's a good thing we caught that though, because here it's actually important that you specify a resolution that is divided.
Jonas,
Yes?
yes.
Is it? I don't think it is, but is it the like the 8 amount of threads? So the first parameter in the shader is like the scale or something, and then the second is the amount of threads you want to run it on.
Maybe. I don't know if I really understood the question, but yes, I think that's what.
So you're dividing by 8 because you're saying, oh, because we're dividing this of 8, like over 8 threads or something?
Yes, you're on to the right track.
Okay.
Yes. Because previously we said non-threads 8, 8, 1. And so that means this program within its group, we'll come back to that term later, it will run 8 by 8 threads running this program.
No.
Yes.
So it runs 16 threads.
64.
Oh,
8
yeah,
times 8.
I know math.
Yes.
Yeah.
Good. So to take a simpler case, because that's exactly what we're doing here. We're dealing with thread groups and threads. And so when we dispatch the thread, we're saying how many thread groups do we need to run this program. And within the shader definition, we say how many threads will this group run. So one thread group in this case will run 64 instances of this program on different threads. Hang along.
Do you guys follow?
This is a difficult one though.
It will be an exam question. By then they will know.
Yeah, but coming back to this, it's all about control and about speed, because depending on your problem, you might be able to define how many groups you need and how many threads you can run on those groups without sort of bottlenecking your GPU. But at the same time, you want to utilize the GPU at its best. So you need to sort of get a high number of threads there, preferably, without asking for too many threads.
So does that mean that you need to know your GPU well?
Well,
I mean, the
yes,
point.
if you're designing computators, you should probably know it.
Yeah.
But in many cases, it's fine to just play around with different numbers and seeing if that one performs better than this one.
Mm.
Because for many cases, it's kind of easy to see that, oh well, if I have this problem, for example, there's only a few sort of configurations I can set up that will run across all the
thread groups.
Units, I guess,
Yeah,
for the problem. So
yeah.
in the case here, the units for the problem is pixels in a shader, or no, pixels in a texture. Sorry.
Right.
Let's go on this.
So fundamentally, it's about understanding your problem, and break is identifying which tasks can be run in parallel, right, without interfering with each other, and see, to what granularity can you decompose it, right?
Yes.
So yeah. Okay.
So Microsoft has a kind of a good chart of just this. You dispatch. In this case, they dispatch 5 by 3 by 2. In Unity, you can't use the third axis. You can only use the two axes, so X and Y, but not Z. But in the same sense, you could have, like, you dispatch, for example, in Unity, you would dispatch 5 by 3, for example, and you'd have a thread group table looking like this. And within this thread group, you will have, based on what you call or what you specified within your shader, the num threads being, in this case, 10 by 8 by 3. But in Unity, the same applies here. You can't have a third axis, so 10 by 8, or you probably scale out the problem into the different axes. A bit more simpler case is this one, where you have, let's say this is a texture of 9 by 9 units of pixels. You could divide the problem into running 3 by 3. So you have a thread group here, 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 and here, and here. And then you'd run a dispatch with 3 and 3. But seeing as this is a really small problem, one more feasible way would probably be this, because it's very likely that you'll be able to run just the one thread group with a lot of threads in it. So 81, right? In this case. And then you just dispatch with one thread group.
Right.
Was that any clearer?
It's important to know the architectural differences there, right? So you're kind of working a lot closer to the hardware in the sense that you need to know what's happening under the hood, and you need to figure out what you use compute shaders for, right? So and how you best structure and conceptualize your problems so you can use compute shaders effectively anyway, right? So thinking about small executional units, for example, right?
Yeah.
So
it's how you structure the problem and how you parallelize the task. Speaking of parallels, this slide is from your other course, the mobile one, right? Have you covered this yet?
yeah, we covered that, but technical slide is from Kronos, so
yes.
stolen from there. So, but it's good because that's the OpenGL people, right? So
yes.
they came up with OpenCL, right? So as the OpenGL equivalent for GPU programming, right? So and the concept is fundamentally the same, right? It's all about knowing the hardware structure. But floor is yours.
I don't know if you wanted to say anything about this. I I just sort of copied the pages in.
Right.
Recap covered basically.
Yeah, you covered the essence, right? So it's really about looking at, if you go one back, you can kind of see it, that you have basically access to all the buffers, right? So uniforms, texture buffer, image buffer, and all that stuff. And the main thing is there, you can do pretty much any processing you want to do. You just need to have sufficiently fine granular operations. Then you distribute those operations, you organize them in thread work groups, as it's shown here in the dispatch. And then they are actually, scheduled in the GPU. You can't really control that one, but you're organizing the groups of threads, so meaning they have uniform activities, and then dispatch them to the GPU. And everything that's happening is kind of written back into the buffers. So you can afterwards access the image buffer and do stuff with this. And if you think about it abstractly, it doesn't mean that it needs to be graphics operations or graphics related operation, but can be any mathematical operation fundamentally, right? But of course, what I was talking about here is that most likely it's reflected back in, some sort of output for the graphics card. But this is fundamentally the principle there, right? So it's always breaking down. And on the other hand, for you as a developer, thinking about structure and organizing this hierarchically so you can actually systematically access and use it, right? Yeah, just to get the intuition right. Because if you do GPU programming, you end up there again, definitely, right? So whether it's in graphics, in mobile, if you don't want to mine cryptocurrency and write your own miner for that one, or, we don't know yet. So
I would recommend looking into OpenCL or sort of
right, that's a good one.
Direct computing language, because you really get a good appreciation of how the data actually flows between your GPU and the program that you're writing. And I would also say that, considering that Vulkan is sort of requires more setup than OpenGL, for me, OpenCL was a sort of good step to having the understanding Vulkan more, because it sort of has, to a certain degree, some of the same basic ideas of like scheduling jobs, etc., and sort of having more control over the low-level memory flow.
Yes, future demo time. And well, first off, I could probably show this if it even shows up. I don't think that's not visible at all, is it?
You can try zooming in.
There's
well,
green stuff.
It's not the interesting shader at least, so let's go to this. As I think I said this, compute shaders aren't necessarily used for graphics. So in this case, I have all of these units, cubes, running around based on just random inputs, or not random actually, I think it's based on a noise. So noised input, and so they're just running on the thing. And then I tried to paint behind them, a trail behind them, but there's this thing called texture clipping that you also need to deal with in this case, which I haven't dealt with just this specific thing. But that's just clipping on the y-axis, I think, and it should be fun. So, or x-axis actually. Another one, if it starts from the beginning, that's me by the way. It's more interesting. There we go. So here I started off with a picture, and then I said, okay, all of these pixels scatter around randomly. And then they all had stored, before starting the compute shaders, they've stored their original position. And so I could tell them to run to their home and construct the final picture again. I also added some noise here just to sort of experiment with that. So I think I used a normal map from my face just to get sort of these weird rivers, I guess, of my facial features.
Right.
Then there's just a random hurling noise movement thing. It looks better from the start, so yeah, there we go. Pretty much the same as the previous noise thing, with the cubes running around on the plane. And then there's the big one, which is terrain generation. This is the one I've been using compute shaders for most, because that's, I can get lost in just playing around with values and trying different noise functions and stuff. So yeah, this one isn't the best I've written, but we'll go into a better one afterwards and look at that. So to Unity and look at the sample. So we had this shader from the slides. We can run first just to show what it's actually doing. So before that, can anyone guess what it's doing? Or read through the program to get what it's doing? So there's an interesting thing here I don't think I've covered yet, is the ID thing. That's basically, if I have the slides somewhere, yeah, it's specified what these inputs you can give to the compute shaders are. So SV dispatch thread ID is basically an index to a specific thread, considering the whole execution of the thread. So it's sort of across the different thread groups as well. And in textures, that makes a lot of sense because we need to specify that, oh, we're accessing this specific pixel as opposed to this specific pixel within the thread group. So in this case, we're getting the ID and then we divide by the texture resolution in order to get the normalized value between 0 and 1. So in other words, it's a coordinate. And then we just say that the result at this specific index, this is also kind of a weird one because you're accessing a texture with 2 coordinates at the same time. But that makes sense because it's a 2D buffer, so you could potentially just go into the specific index in a 2D dimension. And so if you run it, you'll end up with a texture just showing you the coordinates, which is kind of boring and not really what you normally use compute shaders for, because, well, why wouldn't you do this in vertex shading instead? Or no, fragment shading. So if we go into a more advanced example with terrain, we'll get to really show off the power of compute shaders, I think. So we have a rather large terrain here. This is just running on my laptop, by the way, so I think the resolution of this is 258 by 258 or 248. 2048, right? So
yeah.
Power of 2. This is important, as mentioned by, you mentioned the thing about dividing by
8, and you could lose detail.
Yes.
If you weren't careful.
Yes. So in this case, I'll specify that, let's see, where's the kernel? There we go. So the kernel runs by 16, 16 but divided by 16, 16 by 16. So anyone good at math? 16 times 16.
16.
That's like, that's a lot, right? It's 256, I think, right? Or more, maybe more.
56.
Let's do 56. Okay, good. So in this case, the terrain needs to be divisible in those axes, and in this case, that's the case. That's also a restriction on Unity terrains. You don't operate on, or you operate on a height map of a power of 2 plus 1 because we need another vertex on the end. But we're not dealing with that vertex now because it's a hassle. So instead we'll just be dealing with power of 2 because that works well with our compute shader. So just looking at the results we'll get from this compute shaders. Let's see. Oh, that's not really interesting at all. Oh, right. There we go. I need to generate. So here's the really weird going backwards while we're increasing zoom. So yeah, this is a terrain with both valleys and increases. So I'd say a more realistic looking terrain than the one I previously showed. And yeah, the terrain generator is just sort of doing the same as the previous script. It's hooking up, it's getting the compute shader, its resolution, offset and stuff. Offset is actually used just to see the randomness of the generation. And then you have all the kernels being brought in. So in this case, I'm using a height buffer, so just the buffer as opposed to a texture. And then setting that to be the resolution of the terrain. And I'm just interested in the height, so I'm using a size of floats. And the compute buffer type is structured, but that's sort of default anyway, so I don't really need that. So a compute buffer, I haven't really talked about that, but it's pretty comparable to just a vertex buffer, or a vertex buffer object, where you sort of have, yeah, you have its size and you can have a structure within it. In this case, I only have floats within it, so no need for a structure there, but seeing as comparing it to OpenGL, this is very comparable to where you have like 3 floats for a vertex position, and then you have 3 floats for a normal, and then you have 2 floats for UV. So you can do the same with a compute buffer as well. And so you can sort of deal with all the, you could potentially do all the rendering within a compute buffer or a compute shader if you wanted to. So setting up, yeah, setting the buffer, found the kernel, and then in the update call I just do the same as previously, sort of click around. So whenever I click space, I dispatch, and I dispatch with the resolution of the terrain, so 2048 divided by 16. And as mentioned, this needs to be well, not prone to dividing errors, because then you not run the compute shader on all the terrain, but just a part of it. We can try that after, actually, if you want. Yeah, and then from the buffer, after we dispatch the shader, we just get the heights from the height buffer. So we basically say, okay, height buffer, get the data and fill it into the heights float array. And then I just use the Unity's terrain and set the heights, just passing along those that float array. Within the compute shader itself, there's a lot going on. I've defined quite a lot of different height generators. So we could go through those. We have a random one, we have a noise one, which is sort of derived from that one. And then we have fractal grounding motion, which is sort of another branch from this one. It's more and more expensive as well, but that's sort of what you'd expect with getting better and better results, I guess. Then I have a function where I basically say that instead of going from 0 to 1, I map that curve to go up and down and up again and down again in order to get both increases and values. So that's sort of the only difference here. Instead of running FDM directly, I do this and then run FDM within that. And then lastly, I have another one of those where I sort of smooth out the maximums with the minimums and the minimums with another noise. Yeah, so there's a lot of variations here. Should I go through them, or?
So just for intuition here, the smoother terrain variant, right? Would it lead to a more less rocky landscape and a more smooth landscape, like deserty kind of feel? Or
So Yeah, that's a good point. You could, like, I have this one defined, which is basically just takes what's it called, kernel noise, and using that definition instead, you would get a completely smooth terrain. And so FBM is basically just you stack multiple curly noises on top of each other, but with differing scale, sort of, and different heights. So you get sort of a rough layout of the terrain. That would be this one. It's just very smooth. Then you have another layer on top, which is more the noise is sort of closer together, and you get more of a defined structure of mountains and stuff.
So if you want, you could think about it as a semi-supervised landscape generation, right? By defining the underlying function, for example, like you said, the valley and crease and so on, you get a rough mental idea what it will look like, but of course it's will be slightly different every time, right? So it's kind of a mixed approach of being totally autonomously generated or somewhat guided by intuition.
So I'm not really sure if I should go into this, but so a normal noise function goes from 0 to 1, and so for the creases and valleys variation, as I mentioned, there was a curve and stuff. So if we imagine the noise curve going like this, that's a normal noise. It's either a value of it's a value from 0 to 1. But if we map that noise value into a curve defined differently, which is what I do in the creases and valleys, I say that if it's at 1, that means the height is at 0. But if it's at 0.75 or whatever, it's at max. And then you get, you take control of what the output of the noise means.
Yeah.
And map that into a new.
Right.
Yeah, height.
It's a bit like to the contrast mapping yesterday, as I remember that Ahmed talked about, where they had the pictures where they just left the average signal unchanged, but just spread the amplitude between extremes, right? So this way you can spread or moderate the effect of noise in your case in specific spaces, right, of the model, right? So I mean, I'm not sure, it sounds related anyway.
Yeah.
So, but abstractly, so you kind of control the noise in a wider sense by emphasizing or normalizing it, for example.
That's at the core of generating terrain, I think. Just controlling the noise function and getting the perfect noise function. I'm not yet there, but there's a lot of interesting things you can do with it. Speaking of Ahmed, actually, he probably mentioned the filtering mechanics he used for image recognition, right?
Yeah.
Or computer vision.
Yeah.
So many of the operators you pass you pass on to the video or the feed will actually most likely be running on computers. So the solver operator, for example, where you do edge detection, that's a pretty easy one to define in a computer, where you have the spread groups going over the image sort of that.
Right.
Yeah. Comparing each other.
Yeah, good point actually, good application for that, you're right. I mean, for performance point of view, right? Because you want to be close to real time in this particular case, so you have the edge of performance.
I have a few more slides just to wrap it up, I think. Appreciate this in Unity demo time. Yeah. Inspiration. So, yet again, terrain. The GIF I have down there is basically just what I've shown you, but I also mapped time into the noise function, and it looks cool.
It does.
The one above is another application of using compute shaders, where you don't directly work on a 2D sort of platform, but because the terrain is basically you have a 2D texture, you could see that like that's what a height map is, right? You have a 2D texture and then you map the heights to the pixel value. and the terrain is basically just a direct translation of the height map into 3 dimensions instead. But the one above is another use of compute shaders entirely, because you don't, that's sort of, you have a generated terrain, and then you do particles simulation onto your terrain. So in that case, they've done hydraulic erosion, where they basically using compute shader that simulates water droplets, and those water droplets can carry a certain amount of dirt, basically, and move it along in the terrain, and that way you get more realistic looking terrain with, erosion.
Cool.
Then there's a few other examples as well that I just found yesterday. The one with GPU voxelization seemed pretty cool, I thought, so I included it. I don't know really how they do it, but it's doing it on the compute shader, so it's really interesting, I think. And then there's also GPU sorting, which is kind of similar to the previous example I showed, where the pixels, in this case, they don't know where they need to be, but they can compare with their neighbors in order to find where they should be.
Cool.
And they do it in parallel, so it's cool.
Nice.
Yes.
So the hydraulic erosion, right, that would be a classical 2-pass model, right? So where you have the first pass, you generate the terrain,
Yes.
and the second pass, you would do the artificial erosion, right, the
Yeah.
hydraulic erosion.
A cool thing to consider there is actually how you define the thread layout. So do you have particles running in 2D like the non-threads, or do you have a lot of particles in the x-axis and then, or threads in the x-axis and then none in the y-axis? Because there's no like direct translation of how you define particles in the thread space.
Yeah.
So I think for those kind of cases where you have particle simulation, you don't really use the different axes in the both thread groups and the thread non-threads definition. You just say, okay, we run 600 particles in the x-axis, and that's this thread group. And that's what I think we did in that example as well. Yeah.
Cool.
That's the end.
Cool. Sweet. Thank you very much. That's a fairly intense overview, right? Both including theory and practice and specifics of Unity and more general compute shaders and so on, right? So, questions from you guys, I guess. No questions, or better not?
Could you potentially see a use case for?
Yeah.
Yes, you have a question
What's the
first.
most difficult thing about understanding this according to you?
Definitely the non-threads thing. Just getting. I mean, I kind of understand it now, but it's still difficult to see how you would properly define what makes sense for a compute shader. Because in some cases with like textures, it kind of makes sense to utilize multiple axes for the thread group. But in other cases, it's sort of, it seems ambiguous to me. So, yeah.
Are there frameworks to test that automatically? Sorry, in case. Like, because I would imagine you could just parameterize them systematically and explore the parameter space.
I would guess so, but I haven't seen any. I haven't looked into it.
Right. Okay. Yeah.
Yes, as I was asking, does anyone have an idea for what they would kind of be interested to looking into for compute shaders? If you were looking into compute shaders, very long question, I know.
Try to use it, try to figure out how to use it to try to model that map of mine, because I have a map of our world and it seems to be something that should be used potentially for model effects.
Yeah, that would be interesting to see.
Yeah. Plus then you can run secondary effects on it, right? Sorry.
Just a question on the side. For the compute shaders, then you're still using the sort of HLSL syntax. You're not doing everything extra.
So all the library functions you will use, so like apps, that's HLSL, and that's the same you use in Unity's HLSL normal shaders. There's a few things to be aware of there, because some of the functions aren't entirely implemented within Unity's framework. So for example, the noise function, which is normally defined from HLSL, is not accessible, so you need to define your own noise function.
If you go to doing sort of GPU programming, you will find that you're super restricted in what you can and can't do. It's the same with OpenCL. They say, like, you know, because when you do OpenCL, you're basically writing what they call OpenCL-C for your kernels, and that's basically like OpenCL, or it's sort of like C without recursion, without dynamic memory allocation, without function pointers, and as soon as you sort of lose that, then you lose a lot of stuff that was really convenient. Suddenly, yeah, so, yeah, it's the same with computer shaders. Probably also an even smaller set, since they're still sort of thought to be used in a graphics related context as opposed to general computations where you have OpenCL.
Is the overhead of branch prediction as taxing as it is the vertex in Python shader?
I haven't looked into that, but I mean, I guess that's the case.
Yeah.
That you'll often find that compute shader is branching. Actually, a cool thing to note about that. There's some specifics. There's some include file somewhere. Yeah, so seeing as you might need loops and ifs and whatnot in your shaders, there's added syntax for optimizing this further. So in this case, I'm unrolling the for loop. So you don't actually have a for loop that the program is running, but when it's compiled, it unrolls the for loop for the number of octaves in this case, so 6 times. Instead of having a for loop run 6 times, it basically just says, okay, run this piece of code, run this piece of code, run this piece of code. So yeah, just flattening out the for loop into sequential code.
So and then also the synchronization then is managed by DirectX in this case itself, right? So by because the integration in the value, for example, right, so it needs to be synchronized fundamentally. So that's kind of hidden away from you as well, right? Because so you're calculating this thing, you're spreading out the different noise input, and then you are running this in parallel.
No,
you're basically copy pasting the loop 6 times. Or
okay.
the context of the loop.
Right.
Yes.
Okay, that's cheap. Yeah. Okay.
Yeah.
Right.
But that's passive.
Yeah.
Yeah.
There's a few different attributes you can put on.
Right.
Stuff gets weird when you're doing GPU programming. So you, so for instance, I know in OpenCL you program with this sort of model in mind that you're essentially running a set number of cores at the same time for a function, and they share the same instruction pointer, meaning that, you know, for each line of code that you run in your current function, that is sort of executed on 6 cores at once, which certainly explains why stuff like branch or doing if statements is super or is very costly, because what will happen is that if you say you have an if statement and you have sort of one of your items in your group is going to trigger that if statement, then that operation will still be sort of executed for the next, or for the remaining sort of 7 items within one working group. Although the result won't be saved, but it will still be executed to maintain sort of the essentially to maintain that those groups are still running in sort of sharing the instruction pointer. Which means that if you have an if-else case and you both trigger the if statement and the else statement, then you're essentially doing both the computations, which obviously sort of impacts performance. So in the GPU world, stuff like that gets a bit weird quite fast.
Yeah, it's hard to program with that logic.
It's different.
It's different.
To bend your head around it. Is anybody keen doing anything like that for their second project?
I mean, it would be kind of difficult seeing as this is IMT, right?
Well, in general, GPU programming, OpenCI,
Right.
whatever.
Yeah.
Right. So the correct answer is usually no, because it won't help you in the exam. So
Also, I hate saying this, but if you're looking into GPU programming, look into CUDA. I don't really like saying that, but it's just because I prefer using, or I prefer OpenCL since that's actually an open standard. And CUDA is only for NVIDIA specific devices, which means unlike OpenCL, you can't actually run it on your CPU, which you can with OpenCL, which is amazing when you're doing debugging. But there's, there's much more resources on doing CUDA programming than OpenCL programming. When I did this in the course we had before, which was called GPU programming, that was my sort of main problem, was trying to find resources, good resources on the OpenCL stuff. CUDA stuff seems to be way more, have way more resources.
So areas where you would use compute shaders. In games, there's AI, there's physics, there's graphics, of course, general purpose use, like for algorithms, I guess, specifically algorithms that can be parallelized. Yeah, the case where I mentioned previously, where you have sort of these image convolutions running, which I think Ahmed is more familiar with. All of them are.
yeah, vision in general, right? So
Yeah.
recognition. Yeah. So
Your imagination, or your
so when
imagination.
shouldn't you use compute?
What do you mean?
When should you not use?
Okay. Well, when it's easier to run it on a normal shader, I guess. So image effects, I've seen a lot of people running image effects in both fragment shaders and compute shaders, but there's a certain overhead when you're actually outputting the data directly to the screen. So if you're actually running post-processing effects on the viewport, then it's probably more efficient to run those using fragment shaders, because you don't need to sort of get out of the context of rendering to the screen before you get in back again.
Yeah.
Because using compute shaders in that case would require you to set up a render texture and get the texture from the screen and putting it back in there. So
It's like
not as efficient, but it's
Right.
an option as well. Another one would be probably not parallelizable problems. So
Heterogeneous computing.
Huh?
Like heterogeneous computing. If you're not if the stuff you're doing is homogeneous, then you can put it on a GPU.
Yeah.
But if it's not, then it's probably not worth the time,
Yeah.
and might also slow you down.
So an example I have is, I'm doing simulations as well, social simulations they're called. So the idea is you model individuals, right? So a bit like AI, right? Problem is, if individuals interact, the outcome is unpredictable, right? So that's the key about those simulations. So there's a lot of conditions. Conditional execution and interaction. Not in the action in the sense I'm checking my neighbor's properties, but in the sense I'm interacting and getting unknown feedback I need to process. And that is like the deal breakers per se. So you stick to CPU programming, in fact. And that's it, because I was looking to that as an option as well. GPUs, and that you can forget that. So if you have non-interacting, or at least predictable, yeah, exactly. If you have predictable deterministic interactions amongst particles, environment, I mean, your environmental modeling is perfect, right? Terrain modeling is of course perfect. Then it's very suitable. But if you want to model humans, for example, yeah, good luck. So it's not necessarily the way to go. So. Cool. Well, thank you very much. I think we'll leave it at that. Appreciate it. Yes. Your offset of time is duly noted, so as usual.